How's it going, ladies and gentlemen? Mr. Donnie here again. This time taking a look at 25.1 stuff, organic molecule, and their properties. So our objectives are going to be to describe the structure and properties of organic molecules, including acidity and solubility. All right, so organic molecule structure. Let's start there because structure has everything to do with function and its properties. So organic molecules have carbon, and they're bonded together. So I got carbons bonded together, and I'll start with a simple, just an alkane, and it looks like this. It's carbon, 4 carbon chains, and on each of those carbons are hydrogens. So the question that we want to talk about is, well, what shape is each carbon going to make? Well, I know that carbon, in order to make 4 bonds, needs to have sp3 hybridization. So that is going to give you the tetrahedral shape, which is going to give you a bond angles of 109.5 degrees. So you're going to get a tetrahedral shape, right, with these, which means that these carbon bonds aren't really going to be straight lines. They're going to look kind of more like this, like kinked chains when everything gets linked together. All right. It's pretty much a carbon backbone with a hydrogen skin. So we got carbon in the middle. It's serving as the backbone for the structure, and along the outside of it, the skin is hydrogen. So if you're thinking about reactivity and stuff, you got to take a look at what's on the outside, because it's on. This is one of those weird. Yes, the outside does matter, right? Because that's what's exposed to everything. This isn't life. This is chemistry, okay? And the outside does matter. The hydrogen is like the skin. It's the outside. It's what is open to reactivity if you're trying to get a chemical reaction to occur. All right, so stability of organics. Carbon bonds with itself pretty readily. It wants to make 4 bonds. It can make carbon chains as long as you can imagine. It also bonds with hydrogen readily. And when carbon and hydrogen bond, or when carbon bonds with carbon, you get a nonpolar bond, and therefore it's relatively unreactive. If we're taking a look at this image over here, it's an image showing the electrostatic potential. It's basically showing you where charge is, and you can see that it's pretty evenly distributed, right? There's a little bit of blue here and a little bit of red, but they're pretty much the same charge throughout the whole molecule, which means it's not going to be very reactive. It's when things have a big difference in charge that is going to make them reactive. Also, a little pet peeve of mine, I'll get into that, but functional groups, okay? They determine how a molecule will behave or function. So you can see that here methane doesn't have any great difference in charge throughout the molecule, where here, because of this double bond O, you can see this area is really negative and this area is really positive. This molecule is going to be a lot more reactive than methane, this molecule over here, because of that uneven distribution of charge. So this double bond O is what we call a functional group or a family, because it is going to determine how that molecule functions. It makes it different. All right, so other properties. It will depend on what functional groups are present. If there are no functional groups, then it's going to be nonpolar, not very reactive. If you add a functional group, you can change its solubility. You can also change its acidic or basic behavior depending on what functional group is added. So let's take a look at some of this. So solubility. Organics tend to be long chains of carbons. They're going to be nonpolar molecules, right? So if I'm making this long chain of carbons and bonding with hydrogens, those are all nonpolar bonds. My whole molecule is going to be nonpolar, which means it's going to be soluble in nonpolar solvents, meaning it won't be soluble in polar solvents like water. This is my pet peeve. This is why water and oil don't mix. It's not density. People get that confused and say, oh, well, they don't mix because oil's got a different density than water. No, they don't mix because water is polar and oil is nonpolar. So they're not going to interact because the oil is nonpolar. There's no charges for the water to interact with. The water is polar, it wants charges to interact with. Oil will be soluble in nonpolar solvents. Okay, so that's why. Why does oil float? Because it is less dense. But the reason they don't mix is because they have different polarities. Remember the old adage, like dissolves like, right? So they have to have similar polarities or attractive forces in order to dissolve in each other. Alright, so if I'm taking a look at this organic molecule, I've added a bunch of functional groups, I've added a bunch of OH groups, and the OH groups are going to make it polar. So if a polar or ionic functional group is added, the molecule may be soluble in polar solvents. So this right here is sugar, it's glucose, and I know that you can dissolve sugar into water because I drink sugar beverages quite frequently. You know, lemonade, soda, Kool-Aid, whatever it is, it's sugar dissolved in water. So sugar is an organic molecule, and the reason that it's soluble in water is because of the functional groups that are on it. All right, so what's really interesting is different parts of the molecule can behave differently. So if I'm taking a look at this molecule, I can kind of break it up into two different parts. So this part right here is nonpolar. It's just a long carbon chain, and then this end is really polar. It's even ionic. So this end will dissolve in water. So that end is water soluble, and this end is not water soluble. So this is how soap works. This is sodium stearate. This is in soap. This is how things clean. Well, I know what's dirt. Dirt is nonpolar gunk. That is where it shouldn't be. So how do I get rid of it? Well, I could dissolve it in nonpolar bits, but then I need to be able to wash it away with water, and that's where this end comes. And what happens really, really neat. So I'm kind of repurposing this picture. So I have this surfactant molecule, which is like my soap. So here, this end is water soluble, right? It's polar. And then this end right here is not. It's non-polar. So what happens is, if you got some dirt, say this is the dirt, a stain on your favorite shirt or something, you go, all right, well, how am I going to get rid of it? You add some soap, and the soap is going to attack it. So the part that's non-polar, the part that's only soluble in non-polar, is going to surround the dirt, and the part that's soluble in water is going to be on the outside. And now that's when water can surround the outside of it, that part that's water soluble, and the inside is not water soluble. This is your dirt. So you got the non-polar dirt being surrounded by the soap molecule, where the outside of the soap molecule is water soluble. So now that whole thing forms what you call a micelle, and that the whole thing can be carried off and washed away into the water, and you end up with a clean shirt. Pretty neat. All right. You can also change the properties of organic molecules with some acidic or basic groups. So this is a carboxylic acid group, and what happens is this hydrogen can get kicked off because of this double bond O. Once that hydrogen gets kicked off, you end up with a molecule that has resonance, because that double bond O can be on this O or that O, and it doesn't matter, they're equally good. So once you get rid of that hydrogen, it's still really stable without it, which is why this OH group is actually an acidic group and not a basic group. You'd be like, oh, OH minus hydroxide ion, right? No, that's not what ionizes. What ionizes is just the hydrogen, leaving the oxygen behind. So you can make organic molecule acidic with a carboxylic acid group, or you can make it basic with an amine group, right? So that's an amine group. And why it's basic is because that nitrogen has unshared pair of electrons that can be used as a base and make a bond with other things, making it basic. Okay? So, yeah. Boiling and melting points. So, since hydrocarbons tend to be nonpolar, the strength of their attractive forces are determined by the extent of London dispersion forces. So, basically, it's just that instantaneous, momentary attraction from the electrons being on one end of the molecule for a moment, and more so than the other. So the bigger the molecule, the stronger the attractive forces, and the greater the melting and the boiling points tend to be. So here I have methane, which is a gas at room temperature, and here I have pentane, which is not. So if we take a look at some of the boiling points for these, methane's boiling point is negative 161 degrees Celsius, whereas pentane's is a positive 36 degrees Celsius. So the reason for that is, well, we got more mass, we got more electrons, so we can have stronger attractive forces in pentane as opposed to methane. So summarize, what can you say about the structure of organic molecules? What can you say about the reactivity of organic molecules? What can you say about the properties of organic molecules, all right? So I hope you found that helpful. I'll see you in class. Bring questions.